Just a reminder that the recording has started, and Waterloop, you can start presenting.
Thank you. Hi everyone, my name is Quinn Hodges. I'm the lead of the communications team at Waterloop, the University of Waterloo's Hyperloop design team. Today I'll be walking you through the design process of our CAN library. Along with showcasing my team's work from the past 8 months, I'll also hope that I'll be able to teach those unfamiliar with the domain a bit about communication systems in general and give you all some insight into the design decisions that we made and why we made them. Without further ado, let's hop into the presentation. I'll start out by outlining the problem statement, including the functional and non-functional requirements for our system. I'll give a brief description of each of them before moving on to outlining the design space and walking through each of the decisions that we made. Lastly, I'll chat about the final design and the possibility for iterations moving forward. The goal for our communication system was to design a communication system that meets the following criteria. It needs to be reliable and connectionless. It needs to have a high transfer rate to support one of the requirements for our pod, which is disabled by default. It needs to be compatible with our existing hardware. This includes STM32 microcontrollers and a Robotech motor controller. Along with these functional requirements, it also needs to include a physical layer, which is space efficient and easy to implement, as well as an API layer, which is modular and easy to extend. So what is reliability? Reliable communication gives the guarantee that messages will reach their destination complete, uncorrupted, and in the order they were sent. So why do we need reliable communication? Having a reliable system simplifies the internals of the API which we provide to our firmware developers in 2 ways. First, when they send a message, they know that all the other boards will receive it. And second, when they receive a message, they know that is the most up-to-date information available, and this is without us having to track anything like message timestamps to figure out if a message is arriving, whether or not it is actually the most recent message. Our next requirement is that it's connectionless. So what does it mean for a system to be connectionless? A connectionless communication system is best described as what it's not, and that's to say it's not a connection-based system. A connection-based system is a system which requires some form of handshaking between the sender and receiver before the transmission of data takes place, as well as an acknowledgement from the receiver that the data has been received. A connectionless system, on the other hand, is one which does not require this handshaking. So that means that data messages can be sent between devices without requiring the receiver to inform the sender that it's ready to receive data or that it has received the data. So why is it important for our system to be connectionless? Since we have control of all of the devices in our system, we can always assume that every device is going to be ready to receive data. This means that a connection-based protocol would add unnecessary overhead by sending the handshake and acknowledgement messages. Removing this overhead enables us to increase the amount of actual data that our pod is sending between devices. So what does it mean for our pod to be disabled by default? Disabled by default is the premise that in the absence of active control, our pod will regress to the resting state. In terms of our communication system, this means that every single device in the pod needs to periodically and persistently send data to notify all other systems in the pod that it's still working. You can think of this like a heartbeat for each device. If a device fails to do so, then the rest of the pod will assume that it has failed and will enter into an emergency shutdown procedure. Having a high transfer rate means that we can reduce the period between the messages that each of the boards send and allows us to detect errors faster, making your pod safer. In order for our communication system to be usable, it needs to be able to interface with both STM32 microcontrollers, which drive our embedded boards, as well as our Robotech motor controller, which drives our motor. If we were to design a communication system that didn't do this, then it would effectively mean that we'd either have to redesign the communication system or redesign our pod, which are both things that we really wouldn't want to do. We also have a few physical requirements. So when we're designing systems in general, we want to do so in ways that make the life of the person implementing the designs as painless as possible. Designing a communication system is no different. Most of the work I do is on the software side of the system, and this means that I'm going to need some help working with members of the electrical team to implement the physical layer of the system. I'd like to think I'm in pretty good terms with them, and so I'd like not to change that by poor design choices that make their life horrible when they try to implement it. Space efficiency is another aspect that we need to consider for the physical implementation of our system. Our pod is only so big, so the less space we take up with the physical layer of our system, the easier it will be for other engineers on our team to access portions of the pod like pneumatic valves and board mounts. In order to make it easy for our firmware developers to send and receive messages from their respective boards, we need to be able to provide them with a library that can be easily imported into their projects. We also need a design that will be easily extended both in terms of supported functionality and supported boards. Now that we know the requirements, let's get into the design process. The first place to start in terms of the design process is looking at existing communication protocols. After doing some research on the internet, we found 3 technologies that others have used in similar circumstances. Those were Ethernet, CAN, and FlexRay. In order to compare these technologies, we built a matrix against our functional requirements. From this matrix, we can see that there's only one option that matches our requirements. That was CAN. This is not to say that there isn't competition for future iterations. As we develop our custom motor controller, the requirement for Robotech compatibility will be dropped, and we'll need to revisit this matrix and determine if we need to move towards a faster protocol. It's also worth noting that while the UDP Ethernet protocol is not natively reliable, should we want to choose this option in the future, we have the ability to build reliability into the protocol with additional software. That's not to say that it wouldn't be difficult, but it is possible. The next design decision that we need to make is what device topology we're going to use. So here are 4 common network topologies, which include the mesh, the ring, the bus, and the star. Just like with communication protocols, each of these topologies has its own advantages and disadvantages. For example, the mesh topology is very good for concurrent communication between devices because there's no shared medium and all of the devices are able to talk to each other. The ring topology is great because there's no chance for messages to collide with each other. Unfortunately, because of the way that it's set up, it's very difficult for a device to talk to a device on the other end of the ring. Star topology, very much like the ring topology, is very easy for devices to talk to each other, but it requires a central arbiter called a forwarder, which sits in between devices. And this needs to be specialized hardware that not all communication protocols support. And lastly, we have the bus topology, where all of the devices are able to talk to each other by sharing one common bus. Since we're using the CAN protocol, we'll be going with a bus topology. Built into the CAN protocol is a collision avoidance procedure, which enables devices to communicate effectively with each other on the bus. This means that if one device is sending, then no other devices will try to send a message which would collide with the message that the first device was sending. Without this procedure that's built into the CAN protocol, we would likely use a star-based technology, since we'd probably be using either Ethernet or FlexRay, which both support the forwarder. Moving on to program language considerations. A few years ago, this likely would not have been a question. We would have chosen C++, given that it was the only popular systems programming language that didn't compile down to a virtual machine like Java or Python or C#. Nowadays, though, we need to consider that Rust may be a viable option. Rust provides a lot of useful utility, including segregating unsafe code and compile time memory management. And while in recent years there has been a big push for building open source crates for Rust to interface with STM32 MCUs, the majority of our codebase is currently written in C++. Thus, to ensure that we provide an easy-to-include library for our firmware developers, we've chosen C++ as the language of choice for our firmware library. To reiterate, our final solution is a CANBUS-based communication system, which includes an STM32 compatible software library. So where do we go from here? Well, a few places. We're currently working on an over-the-air bootloader, which will enable us to remotely flash boards using the CANBUS without having to hook onto the pod. Our team is also moving over to RTOS, which means that we'll be converting our CAN library into RTOS task, which is able to track the messages coming from each board due to our disabled by default design. This will further reduce the complexity of integrating our embedded boards with the CAN system, as it will no longer be required to implement the state tracking themselves. Finally, we will also be investigating the feasibility of moving away from CAN to a more advanced protocol as our pod systems become more complex in the future. So now we can move over to questions.
Yep, as said before, thank you, Waterloop, for presenting, and questions can be on the chat or you can raise your hand.
I believe they're the F4 series, but we use a couple different ones.